Imagine seeing a rock that looks like it was painted with tiny leopard spots, right there on Mars. That strange pattern turned a routine rover drive into one of the most exciting scientific puzzles of our time. Today, NASA's Perseverance rover found a leopard-spotted mudstone in Jezero crater, and scientists say it may be the clearest sign yet of ancient microbial activity on the red planet. Stay with me. I'll explain what they found, why it matters, the doubts that remain, and what must happen next to move this discovery from potential to proven. Welcome back to Galaxy Frontier. If you love NASA news, planetary science, and big questions about life beyond Earth, you're in the right place. Today we break down NASA's announcement about the leopard-spotted rock sample, nicknamed Sapphire Canyon. We'll cover where it was found, how Perseverance analyzed it, the chemical and mineral clues, alternative non-biological explanations, and why the Mars sample return mission is the single most important next step. There's also a short bonus near the end. So watch through for a few surprising Mars facts you'll love. Our story begins in Jezero Crater, an ancient lakebed where rivers once flowed and sediments accumulated. NASA chose Jezero because it preserves fine-grained mud and delta deposits, ideal for trapping organics and microfossils. On June 9th last year, Perseverance drove into an inlet channel and spotted a slab of mudstone covered in dozens of dark round spots and ring-shaped textures. Engineers and geologists quickly nicknamed the textures leopard spots and poppy seeds. Those visual cues sent geologists into a careful, excited scramble. Perseverance's imaging systems captured the textures at high resolution. Instruments such as Sherlock and Pixel were deployed to probe composition at microscopic scales. The rover drilled a core, sealed it in a sterile metal tube, and placed it in the cache for future return. That sample, Sapphire Canyon, immediately became a high-priority candidate for Mars sample return. When researchers analyzed the rover's measurements, three overlapping clues jumped out. First, organic molecules were detected concentrated where the spots appear. Second, the rock's textures and sedimentology indicate long-lasting liquid water in a calm, muddy lake environment, exactly the kind of setting where life on Earth thrives. Third, the mineralogy includes vivianite and greigite, minerals often associated on Earth with low-temperature, oxygen-poor environments rich in organic matter. Vivianite commonly forms in wet sediments where organic decay takes place. Greigite can be linked to iron-sulfur reactions often associated with microbial processes. Crucially, these clues aren't isolated. The organics map to the spotty textures, and the minerals match a low-temperature aquatic environment. That co-location, multiple lines of overlapping evidence, is what makes the findings so compelling. On Earth, similar textures and mineral suites are often tied to past microbial activity. Excitement is warranted because the sample contains water evidence, plus organics, plus an energy gradient, the three classic ingredients for habitability. But NASA is deliberately cautious. The team uses the term potential biosignature, meaning this evidence could be biological, but it is not yet conclusive. Why the caution? Because some abiotic, non-living processes can mimic biological signatures. High-temperature alteration, prolonged acid exposure, or catalytic reactions under certain conditions can sometimes produce similar minerals and organics. The team has tested these alternatives thoroughly. For example, vivianite is fragile under heat. If the rock underwent high temperatures, vivianite would be destroyed. Yet vivianite persists, arguing against thermal metamorphism. Olivine, a mineral that breaks down under acid, is also present, making long-term acid leaching unlikely. Scientists are left with a set of observations that strongly favor biological hypotheses, but the scientific method demands more proof. Let's unpack the main non-biological hypotheses. Thermal metamorphism. High heat can rearrange minerals, but the mineral assemblage doesn't fit this scenario. Acidic alteration. Acid would leave telltale indicators and destroy olivine, yet olivine remains. Abiotic catalytic reactions. Catalysts sometimes create organics and minerals, but there's little evidence for the catalysts or conditions needed. After running through these, the team concluded that non-biological paths are possible in theory, but increasingly unlikely given the full suite of chemical, mineral, and textural evidence collected in situ. A deeper look at the tools helps explain why this sample stands out. Sherlock uses UV lasers to excite molecules and read Raman and fluorescence fingerprints, ideal for spotting organics and mineral phases in tiny spots. PIXL performs micro-XRF mapping that tells scientists element by element what the rock contains at millimeter scales. Mastcam and Watson imagers record context and textures. In one sense, these instruments act like eyes and noses at microscopic scale, revealing tiny chemical changes that point to biological or non-biological processes. Science is social. When the team first saw the images, there were late nights, careful calibration checks, and many rounds of peer pressure testing, sending raw data to external experts and independent labs for evaluation. NASA's statement that "we can't find another explanation" is a careful phrase born from consensus and rigorous review, not hype. That's why the announcement matters. It represents agreement among many experts that the data resists simple, abiotic interpretations. To move from potential biosignature to confirmed detection, we must bring the sample home. That's what Mars sample return is built to do. The chain of events. Perseverance caches tubes, a future lander and fetcher collects the tubes, a Mars ascent vehicle launches the cache into orbit, and an Earth return orbiter captures and returns it. Once on Earth, labs with far more capability than any rover can apply ultra-sensitive isotope ratio mass spectrometers, nanoscale imaging, and contamination controls to determine whether the signals are truly Martian and biological. Contamination control is critical. NASA's planetary protection protocols regulate sterilization, handling, and quarantine to prevent Earth microbes from confusing results, and to protect Earth from unknowns. That careful containment is part of why sample return matters so much. From a statistical viewpoint, this single compelling sample updates our beliefs about life on Mars. If multiple, independent samples across diverse environments show consistent biosignatures, confidence will climb rapidly. Philosophically, confirmation of past life on Mars would transform biology and our place in the cosmos. Life would be shown to have arisen more than once in our own solar system. Quick bonus facts for sticking around. Olympus Mons is nearly 3 times taller than Everest. Jezero's ancient delta is a prime place for preserving fossils. And Perseverance's sample tubes are hermetically sealed, stored like tiny time capsules. If you enjoy these deep dives, leave a comment. I'll reply to as many as I can. So, where do we stand? NASA's Leopard-Spotted rock is one of the most exciting potential biosignatures ever found off Earth. The data leans strongly toward biological interpretation, but extraordinary claims require extraordinary evidence. And that evidence arrives when the samples come home. If you found this helpful, please like, subscribe to Galaxy Frontier, and ring the bell. Tell me in the comments, do you think Mars once hosted microbes, or will a clever non-biological explanation win out? Until next time, keep looking up.